In this lecture, we're going to talk about how to create a Lewis dot structure. So let's dive in. So this will be a way of describing covalent bonding, and we call them Lewis structures because it's based on Lewis's bonding theory. So when two atoms are going to share electrons, they're going to have a shared bonding pair of electrons, is what we call it. So those two electrons are what create the bond. It's not going to be one, it's not going to be three, it's going to be two. Now, a double bond, we'll talk about in triple bonds, that'll be 2, 4, or 6. But each bond is going to encapsulate two electrons, and that will create what we call a single bond. So bonding pairs of electrons will be shared between two elements. They're not shared within the whole molecule. These are valence electrons that are attracted to just those two nuclei, and so shared between them. Any lone pairs of electrons in our Lewis structure are going to be non-bonding pairs of electrons. Now, these are going to just be attracted to the one nucleus of the atom that they're a part of, and they're still valence electrons. They're just not participating in a shared electron situation with another atom. And so let's look at the difference between these two. We have bonding pairs and lone pairs. So a lone pair of electrons on this Lewis dot structure of oxygen are there in green, and our bonding ones are there in yellow. So the bonding electrons are shared between the hydrogen and the oxygen, whereas the lone pairs on oxygen, of which there's 2 lone pairs, including 4 electrons total, are going to just be attracted to the oxygen. I'll say really quickly before I move on, once the electrons are shared, so for oxygen, it's going to experience 8 electrons, so it's satisfying an octet rule. But I'll note that hydrogen is only going to have 2, and so it's going to experience what we call the Duet Rule. It's one of our exceptions to the octet rule, and it's really because hydrogen will be most like helium when it has a complete noble gas electron configuration, and helium has only 2 electrons. So this is a special case just for hydrogen. Everything else will follow the octet rule. Let's look at covalent bonds. So multiple covalent bonds. So when an atom shares 2 bonding pairs of electrons, so that would be a total of 4 electrons being shared, that would create a double bond. An example here is between an elemental oxygen, where to make each oxygen feel like it has 8 electrons, it needs to share 4. And so that's going to be equivalent to 2 bonds. And now each of these lines is 2 electrons is what it's representing. So 2 electrons equals 1 line when we're building our Lewis dot structures. Now, if 2 atoms need to share 3 bonding pairs or 6 total electrons, we'll have a triple bond. And so in this case, we still have each of these lines equals 2 electrons, but now we have 3 of them. And so that's 6 shared electrons, as you can see here, between 2 nitrogens. And so our nitrogens are going to share 6 electrons between them, and then they each have 1 lone pair on them. And so this nitrogen is going, each of these nitrogens will feel 2 electrons from the lone pair, and then 6 shared electrons from the bonds, for a total of 8, satisfying the octet rule. So we're going to walk through a strategy for developing a Lewis dot structure when you only know the elements that go into the structure from the chemical formula. There are a couple of ways to do this. I'm going to show you my preferred method, and I have slides for the other method that's taught as well, which I'll talk a little bit about after this. But I think this is the way that produces the most reasonable structures in the easiest way and creates a little bit more structure to the process and a lot less guessing. So I'm gonna do this for NH3. That's gonna be my example one. All right. So first, my first step, you're always going to take a chemical formula and try to build a Lewis dot structure. So step 1 is to draw the electron dot symbols for each element. And these are going to be your puzzle pieces. And that's all we're going to do. We're going to treat this like a puzzle, so it's not a big deal. All right, so I have nitrogen and I have hydrogen. And I've got 3 of these hydrogen atoms. Hydrogen has 1 valence electron, so I'm just going to put 1 electron with it. My elements or my electron dot symbol for nitrogen needs to have 5 valence electrons because it is in the 5th group of the main group elements. So it's going to have 1, 2, 3, 4, 5. Great. Um, so now I'm going to try to determine the number of bonds that are likely to form from each of these. And the way I'm going to predict the number of bonds each element is going to form is based on the number of unpaired electrons I have. So any lone pair on an atom, I'm going to try to leave alone as much as possible, unless I hit kind of one of our exceptions to our bonding process, which will happen. So that lone pair I just highlighted yellow on the nitrogen, I'm going to try to leave that alone through this process. But I'm noticing that I have 1, 2, 3 unpaired electrons on the nitrogen, which means it needs to form a bond and share an electron with another element or multiple bonds. So that way those are paired up. Because to have 8 electrons around my nitrogen, I really need to have 2 on each side to hit that magic number of 8. So this is likely to form 3 bonds. Now the hydrogen has just 1 electron. But hydrogen is different. It follows the Duet rule because helium has only 2 valence electrons. So it's trying to get to 2. So it really needs 1 bond. All right, once I've identified that, then I'm going to place the element that needs the most bonds in the center. That's my starting point. So my starting point here is going to be the nitrogen. So I'm going to redraw this element symbol here in the middle. And you can abbreviate this process a bit when you're doing it yourself. I just want to be as detailed as possible when I'm introducing it. All right, so that's my starting point. Next, I'm going to place elements that need the second most number of bonds around it. And I'm going to connect them between the unpaired electrons. Now, this is a simple case with only 2 different types of elements. And so I'm just going to be going right to hydrogen. That's the next number of bonds I have. But I'll make a note. So I'll show you this for ammonium, and then I'll make a note about multiple bonds. So I'm going to place those and connect them. It's essentially like connecting the dots here. So when I bring this hydrogen to this nitrogen, I'm like, these 2 electrons can form a bond between the 2. And then I'll do that the same with these other unpaired electrons. And it's a way for lining up which elements are likely to form a bond together. And this will hopefully eliminate some of the anxiety that comes with Lewis dot structures of deciding where to place these atoms. So now I can actually draw this as a Lewis dot structure. I keep my lone pair electrons, and we always show the lone pair electrons in a Lewis structure. And then it's traditional to write things as on top of each other, like 2 dots like this between the nitrogen and hydrogen. So they're next to each other rather than in my puzzle piece form. And that's going to give me the Lewis dot structure for ammonium. And I can double check it at this point. I could double check that my nitrogen needs to have 8, and it has, let's go through and highlight these. 1, 2, 3, 4, 5, 6, 7, 8. Great. So I have 8 electrons around my nitrogen, so it's satisfying the octet rule. Each of my hydrogens have 2, so it's satisfying the Duet rule. And that's how I build Lewis dot structures in a very simple form. So what if you have more than just 2 different elements? What if you have some elements that need more than 1 bond? Or what if you need to have multiple bonds? Well, so when we are placing the element in step 3 that needs the second most bonds, I'll put that next to the one that's the first. And so what I'm doing is I'm always working from the element that needs the most bonds out to the one that needs the least. That means I'll place things like hydrogen and halogens like fluorine, chlorine, bromine, iodine last. And so what I want to do when I place my elements that need only 1 bond to them, before I actually start arranging them around, I'm going to do a quick count. And this comes down to number 4, creating multiple bonds until the number of unpaired electrons equals the number of atoms that need 1 bond. So what happens is in this case, for my nitrogen, I had 1, 2, 3 unpaired electrons, and I had 3 hydrogens that needed to be placed. Those perfectly match up. I can do 3 single bonds. If I had 3 unpaired electrons on nitrogen and then only, well, I guess it wouldn't work here. And let's say just 1 hydrogen, or let's say I was working with a different molecule and it had 5 unpaired electrons and I had one element that had only one bond, I would only be able to match it up with one, and I would still have 4 unpaired electrons. So before I add that hydrogen, I'll try to find multiple bonds for those 4 electrons first, and then add my hydrogen last. The double checking that I do, there's 2 ways to do this. You can either count all of your electrons at the beginning that are valence and then count them all at the end and make sure you have the same number. I prefer instead to go element by element and count up the electrons surrounding it and make sure that it has 8. This allows me to identify problems a little bit better. Sometimes we'll have the same number of electrons, but they'll be placed in a way that I still have elements that don't satisfy the octet rule. They either have too many or too few. If I count and make sure everything has 8 or 2 if it's hydrogen, then I'll be able to pinpoint where there's a problem. I'll be able to say, oh no, this nitrogen only has 6. Something's wrong with my structure. And I know there's something wrong with it right here. So I'm going to walk through another couple examples of this. So I'm going to do one that involves just single bonds, and then I'm going to go ahead and do one that involves multiple bonds. All right, so here is chloromethane. That's not the right name. Sorry, it's escaping me. CH3Cl. So what I'm going to do is first recognize what are my puzzle pieces. So I have 1 carbon, and it has 4 valence electrons, so its electron dot symbol would look like this. I have 3 hydrogens, each with 1 electron, and I have 1 chlorine, and that will be like this. All right. So these are my 3 different things I have to work with. Now, my carbon has 4 valence electrons. To get to 8, it needs to get another 4. So it's going to need to share with 4 things or create 4 bonds. My hydrogen is trying to achieve 2, so for the duet rule. So it really needs to make 1 bond. And my chlorine has 7 valence electrons already. It just needs 1 more to get to 8. So it's going to form 1 bond. All right, so that means I'm going to start with my carbon in the center. So I'm building my electron dot symbol. And now I'm going to count that I have 1, 2, 3, 4 unpaired electrons. And I have 3 hydrogen plus 1 chlorine. And these each need 1 bond. So since I have the same number of unpaired electrons in my structure so far, and I have 4 elements that need 1 bond that need to be placed, I could do this all with single bonds. So I'll come around and I'll add these, making sure to keep all of my lone pairs shown. All right, and that's going to be able to place everything. So my carbon now has 8 electrons around it. My chlorine has 8 electrons around it, and each hydrogen has 2. Now, if I want to redraw this, I can draw this in a couple ways to represent a Lewis structure. I can have my electrons in between each of my atoms to show that they're bonded. Or I can use lines to represent 2 electrons in a bond. Like that. And I've got a Lewis structure. Let's look at something with multiple bonds. Let's do HCN, cyanide, or hydrogen cyanide, sorry. Okay, so for this one, I have a hydrogen. I have just 1. I have 1 carbon, and I have 1 nitrogen. Now, my hydrogen needs 1 bond to get to 2. My carbon needs 4 bonds, and my nitrogen needs 3 bonds. It has 5 valence electrons. It needs to get to 8, so it needs to take on 3 more bonds to be able to do that. So I'm going to follow my kind of guidelines, and I'm going to place carbon in the center first because it has the most, it needs the most bonds to it. Now, the element that needs the second most is my nitrogen, so I'll place that second. And I'm just choosing a spot to put it. So what I'm doing here is creating a bond between this carbon and nitrogen already. Now, I'm going to do a quick comparison. I have 1 element that can form 1 bond, and I have 1, 2, 3, 4, 5. I have 5 unpaired electrons. That's not going to work. If I bond my hydrogen in, I'm still going to have 4 unpaired electrons. I won't hit an octet for carbon or for nitrogen. So what I need to do now is actually form multiple bonds. So I'm going to subtract the number of atoms that need 1 bond. Well, that's 1, right? So let me write 1. So I'll have 4 electrons that need to be in multiple bonds. And so I'm going to start connecting those within the molecule itself. So I can see that I only have 2 elements out on my Lewis structure right now. Sometimes you'll have more. So I'm going to choose to match up an electron from a carbon to an electron on the nitrogen to create a new bond. All right. And then I'm going to do the same thing. I can match up these ones right here. So if I pair up 2 electrons from nitrogen and 2 electrons from carbon, I'll be able to satisfy my octet rule. And that's going to leave just 1 electron here to be able to bond with the hydrogen. And so redrawing this is going to look like 6 shared electrons between my carbon and nitrogen. I still have a lone pair on my nitrogen. Here, I'll make this really obvious that it's in the same spot. And then I'm going to bring in my hydrogen to form that last bond with the carbon. So looking at this, I could see for my carbon, right? I have 2 between it and hydrogen, and I have 6 between it and nitrogen for a total of 8. If I look at my hydrogen, it has 2, 1 from hydrogen, 1 from carbon, so it's meeting its duet rule. And if I look at nitrogen, it has 6 shared with carbon plus 2 on its lone pair, so it also has 8. So this meets the octet rule. And I can redraw this with lines if I prefer. So it's going to look like this, where each line represents 2 electrons. So that's my strategy for solving Lewis dot structures. I think it works fantastically. It creates a pattern of how to do things that just sets like an order that allows you to lean on those rules when you're feeling confused about a large Lewis structure. Now, here's another method that I know is, I think, in our lab notebook probably, and it's all over videos all over the place, and it's a common way of teaching Lewis structures in an introductory chemistry course. And the reason I don't teach it this way is it requires knowing formal charges to evaluate the reasonability of your structure right away. And since we haven't even talked about that yet, it's a later part of this lecture series. I like having a method that gets us to a reasonable structure even without the formal charges as much as possible. So in this strategy, you look at the atoms that you have and count up the total number of valence electrons for each of those elements. So for CH3Cl, we would have 14 valence electrons. 4 are coming from the hydrogen, 3 are coming from 4 are coming from the carbon, 3 are coming from the hydrogen because we have 3 hydrogens, 1 each. And then we have 7 coming from our chlorine for 14. Now you arrange the atoms next to each other in the order that you think they might be bonded together. And to me, this part right here is really confusing because it requires some chemical intuition. If you've seen a lot of molecules, if you've taken organic chemistry, you'll have an intuitive sense about the way atoms tend to group together in organic compounds. We haven't really done that yet. So I feel like this step is just a lot of guessing. Typically, you put your least electronegative in the center, although sometimes some places say your most electronegative. I'm not sure. So then you place your hydrogens and your halogen elements in the periphery because they're only going to form 1 bond. You take all your valence electrons and you make sure that they're the total, like you'll put that same number into your Lewis structure, and you arrange the electrons then around the atoms. And you'll place 2 in between every atom that you think is bonded together. And then you'll put lone pairs around elements as well. And then you can put in multiple bonds. So the problem I have with this piece of it is that students typically forget how many lone pairs something would likely have. And so they'll add lone pairs to elements like carbon, which is very rarely seen with a lone pair and only in an ionic form. It's very reactive. or they'll put more lone pairs than they need in a structure, or, it's hard to know where should the lone pairs go. I think the or the electron dot symbol is a nice guidance on which lone pairs should be where. And then when you're putting in your bonds, it's hard to decide when you need multiple bonds or not. And so I think that this strategy, if you know it and produce great Lewis dot structures with it, keep doing it. If you're learning Lewis dot structures for the first time, or if you're not very confident in your ability to use Lewis dot structures, do not use this method because it involves a lot of guessing and trial and error and intuition that you haven't had time to develop yet. All right, and now I will get off my soapbox and potentially shift